So remember, in experiment you have the whole set of experiments. You have sets, elementary events, and the probabilities of these events. So probability of, so I'm going to call this one to be one experiment with some probabilities of the events well defined, some probability set. This probability, of course, obeys the three axioms of probability. Probability of the whole set is 1. Any probability of any set is non-negative. And if A and B are mutually exclusive, then the probability of their union is the sum of the probabilities. So now I want to combine repeated or combined experiments. So I have another set S2 with, let's say, a probability set P2. So if a typical event here is B, this probability is also well defined. So a typical event here is A. I can call it A1, A2, but I'm just going to leave it like this. So the question is, how do you perform a repeated or a combined experiment? So to be quick, we'll do the Cartesian product. In other words, something from here, something from here. That's what we mean by combining the experiment. So we'll define a bigger space, which is the Cartesian product of the two, which means that any experimental outcome here basically has two outcomes. So one coming from the first one, psi I, and this one coming from this set, eta j. So a typical outcome of this psi belongs to the combined experiment. Of course, if these experiments are repetition, then that comes under the repeated trials. So here the elementary outcome is like this. Once again, elementary outcomes generate events. One event from here, one event from here gives you the combined event, and we want to compute the probabilities of these events. So in a combined space, of course, the A here in S1, naturally, how do you represent in the combined space is going to be, in the combined space, this is going to look like A intersection with the S2. So that, and similarly for B, if B belongs to S2, and then B, or S1 intersection B belongs to this combined set. Oh, but we are going to consider the case where these experiments are independent. So that's when, so the question is, we can define the experimental space or the set of, we can generate the elementary outcomes and sets in this manner. Question is, how do you define probabilities? So we are going to consider for the case where these experiments are independent. So what that means is the probability of, so if I call a typical event here would be, before I move on, a typical event here would look like an event from here and event from here. So A intersection B would belong to the whole, the combined set. So the question is, how do you define the probability of A given? A intersection B. So remember, this intersection is in, not intersection, this notation is in the sense of Cartesian product, A from here and B from here. So if they are independent, we would define this probability to be P1A multiplied by P2B. It's easy to check that this has got all the three probabilities, so you can check from here. This is non-negative. If you put S1, S2 here, this will be 1. And the third one, similarly, you can check. That is, if two events are mutually exclusive, the probability of their union is the sum of the probabilities, where A and C belong to this set S1. And same thing for S2. Same thing can be shown to be here for true for. So this is the way we are going to consider and develop the probabilities for the combined experiment. So remember, this is an event in A intersection. A cross B actually belongs to S, the combined space, which is S1 Cartesian S2 product with S2. And the probabilities, if these are independent experiments, then the probabilities, the product of the probabilities in their respective experiments. So, so now let me repeat this to n experiments. So if S is S1, S2, etc., Sn, and with the events here, psi I, eta j, etc., then if a combined, so A belongs to this, A1, A2 belongs to S2, N belongs to Sn, then the product of their Cartesian product of this event, if these experiments are independent experiments, is going to be the product of the probabilities. So that's the way we are going to approach this. Now consider with this introduction, consider the case where we repeat an experiment where each experiment only has two outcomes, A or A bar. But this is repeated, so there are many times. So I'm going to call it S1, S2, N experiments. So this is like a coin tossing problem, success or failure. In each case, all these probabilities are identical, and they are all independent experiments. And probability of A, PIA, but PIs are the same. I'm going to mark small p. The probability of A bar is, of course, 1 minus PA, which is 1 minus P. I'm going to simply mark it as Q. So remember, when you perform this experiment, an outcome, a typical outcome, will be an interpol here. So it is outcome. So first one could be a head or an A, and then it could be A bar. It will be a sequence like this. So this outcome belongs to the combined experimental space. Yes, S is S1 product, Cartesian product, S2, etc., Sn. So the psi belongs to S. So the question is, what is the probability of this event? So if you look at this event, one interesting thing is we can start counting the number of heads. So if I start counting all the number of experiments, of course, this is going to be n experiments have been conducted. And if I start counting A, I see one head, so head here. So this is I plus 1. Ultimately, I see that there are some k which is less than or equal to n, k heads in this. So this is a sequence of k heads in a specific order. So the question is, what is the probability? So I could even mark it as psi I. So probability of psi I. So remember, this is k heads in a specific order in n trials. So this is going to be, again, we use the same reasoning. These experiments are independent, so these outcomes are independent. So it's the product of the probabilities. Probability of A is small p. Probability of A bar is Q. There are such KAs, and so n minus k Qs. So this is going to be p to the power. So p, Q, P, Q, etc., P, etc., P, Q, P. So since we know how many P's are there, k P's, and Q is n minus k. So this is the probability of this specific sequence. So this sequence is interesting, or has the property that there are k heads in such tosses, in trials. But we know that if you, the same outcome you can create by other rearrangement of this sequence, we will still have k heads, but it will be a different sequence. So this gives us rise to the idea we can ask about a more general event, k heads in n tosses. So if you want to see this pictorially, this is something like a more complicated event created in this bigger space. A, of course, belongs to here. A is not an elementary event because this will be an elementary event. But interesting thing is the A can be written expressed in terms of these elementary events because here things are physical. We know that this sequence has got k heads in n trials. But if I flip these two, I'll get another sequence that also has got k heads in n tosses. If I flip these two, that will be a different sequence. So if I call these sequences to be, so this is a typical psi I can create another sequence, psi j, from here by simply flipping these to a bar, a, then leaving everything else as it is. And so on. So the question is how many, and moreover these sequences are mutually exclusive because one precludes the appearance of the other one at the same time. And it's easy to compute how many such sequences are there because it is a combination, if I call them to be capital N. So let me, first of all, this will be true if either this happens or this happens, etc. This happens. I'm going to call it capital N. So question is how many are there? But all these are mutually exclusive. So it could be this sequence, it could be because of this, or this, or this, or that. All of them have k heads in n tosses. So how many such n's are there? That's a simple combinatorics problem because you have n slots and you have either success or failure, A or A bar. So A can go into the first slot in n different ways. So capital N is going to be, A could go anywhere here, so you have n options. Once a position is filled in anywhere, then the next A could go into any one of the n minus 1 locations, so that's n minus 1, etc. The last one could go to up to here. So these are the options, except the heads these are where all the heads will look identical. So among themselves, this should include those sequences where among themselves they could generate k factorial sequences by the same argument because they have k slots. And if the A's were like A1, A2, etc., AK, by the first one could go in at any one of the k locations, next one k minus 1, etc. So among themselves they could create k factorial sequences, but all of them are identical. So we take care of that, and then whatever is remaining you can write it this way. And this is simply n choose k. So from here, we can say that the probability of A, which is the probability of k heads in n tosses, is the probability of this disjoint union. So that's going to be from the third axiom, the sum of the probabilities. And so all the probability of each such sequence is independent of I somewhere here. So that's going to be simply n multiplied by pkq to the power n minus k. But n is, we just did it, n choose k, pk multiplied by q to the power n minus k. where q is of course 1 minus p. So k is 0, 1, 2, 3, etc. up to n. And I can plot this. So let me call this probability to be, let's say, pk, because it depends on k. So capital Pk. This is not a small p. So that's going to be some value here, some value here, some value 0, 1, 2, 3, etc. So this gives us to, of course, notice that the k is going to be here unknown. All you know is that you're going to toss n times. So another way to represent this is I can define x to be the number of heads in n trials. Then notice that, so if I denote x to be this event, the number of hits in intervals, then this is simply saying that probability of x equal to k. So x is a variable whose outcome is random. So we can call this to be here is an illustration or introduction of a random variable. So that's a variable whose outcome is cannot be determined a priori. But what can be determined is what is the likelihood of it taking specific values in a combined experiment. So the experiment possibilities are 1 through n. So this is the probability of x equal to k. So here we would call x to be a discrete random variable, because x takes discrete values. So x is, just to recall, x is number of heads in n trials. And small p represents the probability of head. So these are the n and the p are the only are the known quantities. So probability of x equal to k is n choose k, small p to the power k, q to the power n minus k, k equal to 0, 1, 2, etc. up to n. So once again, you can plot this. It's going to be typically it's going to look like this. So this is what I have on the y-axis is the probability of x equal to k. So somewhere it peaks. So we can call whatever is this value to be the most likely. It has the maximum probability, right? So if, for example, this particular k has a maximum probability, then we can call this k naught to be the most likely value of. Remember, k represents the number of heads in n tosses. So an interesting question is what is. So in any case, x is, we can call it to be a random variable because its outcome is unpredictable. So this is an example of a random variable. A discrete random variable because it only takes discrete values 0, 1, 2, 3, etc. up to n. So the question is, what is the most likely value of k naught? So to compute that, from the diagram you can see if this is the most likely value, then you get two equations, because if you take the probabilities, so this value corresponds to probability of x equal to k naught. So let's consider two adjacent values. So this equation must be true. Pk naught over Pk naught minus 1 is greater than 1. Right, because that's the larger value. It is also true with the plus here. So we get two equations. So remember, Pk naught is n factorial over n minus k factorial, Pk q to the power. So this is Pk, capital Pk over P, let's say k naught plus minus 1. Q to the power n minus k divided by P, so k naught plus minus 1 is n is the same, so n factorial cancels. So this is Pk naught divided by Pk naught plus minus 1 divided by n minus k naught minus plus 1, right, factorial, k naught plus minus 1 factorial, p to the power k naught plus minus 1. So I'll just do one case. Then let me do the plus case, the top one. In other words, this value over this must be greater than 1. Then q to the power n minus k naught plus minus will become minus plus 1. So if you simplify this, n factorial goes away. And if I so let's say I do this for the previous value, k naught minus 1. So then this would be, I'm taking the bottom value, so it will be k naught plus 1. So this will be n minus k naught plus 1 on the numerator. In the denominator you have k naught goes here, and k naught minus 1 goes up. So you'll have k naught here. Here pk naught minus 1. So p here. Here n minus k naught plus 1. Remember, I'm taking the lower value. So q here. This must be greater than 1. So if I cross multiply this, you get n minus k naught plus 1 multiplied by q is greater than k naught multiplied by 1 minus p. So minus k naught p goes away. This means k naught is less than, look at here, k minus p k naught cancels both the sides. N plus 1 multiplied by p. So k naught is the largest integer smaller than n plus 1 by p. So it's roughly, approximately, k naught is around np. That's what the, so this is the most likely value. You can get one more equation the other way, and so this is the most likely value of the number of heads, for example. And so if you look at this expression, probability of x equal to k, it looks like q to, so it is, this is the probability k equal to 0, 1, 2, 3, etc. And this looks like a typical term in a binomial expansion of a plus b to the power n, right? Because this is simply n choose k, a to the power k, b to the power n minus k. So you can see the, so because of that, this is, we call this to be a binomial random variable. This is binomial expansion. Okay, so, and it also makes sense here because if you can ask the question, if you consider this event, remember x is a random variable which takes the value 0 or 1, etc., or n. But these events are mutually exclusive. Moreover, their whole probability is the probability of the sum, which is probability of x equal to k going from 0 through n. But so if I substitute it here, you get k equal to 0 through n choose k, p to the power k, q to the power n minus k. But this is precisely the binomial expansion, so that of p plus q to the power n, which is 1. So it makes sense that one of these must happen if you perform the experiment. And these are all mutually exclusive. And the binomial name sticks again. So a special case of binomial with n equal to 1 is Bernoulli random variable. So Bernoulli is just a single coin toss. So Bernoulli's probability of x equal to 0 is q, and probability of x equal to 1 is small p. A combined experiment of combined independent Bernoullis give you a binomial. And so we saw the significance of the product NP, which I'll come again later. But the NP is the approximate value of for the most likely value of k, which is the number of heads in tosses. So this leads us to a special case of binomial. So is of interest. So in particular, binomial is the number of heads in n trials, and probability of x equal to k is n choose k, p to the power k, q to the power n minus k, k equal to 0, 1, 2, 3, up to n. Now, what I want to do is I want to consider, we can use this to introduce two other important random variables. So let me consider sort of rare events, which means rare, that means this probability goes to 0. So p goes to 0, except that you have a large number of them. So I'm going to consider the case where n is very large number. So whatever you are looking for is a rare event. And such that, so we are going to consider the case such that their product NP, lambda is a constant. In other words, P goes as 1 over n, etc. That's the whole point. So let's see what happens in this case. So again, we are looking at the probability of x equal to k. So this is a rare event. So this is n choose k, which is n factorial over n minus k factorial, p to the power k, q to the power n minus k. So this, of course, I can write it as n multiplied by n minus 1 p to the power. So I'm going to introduce an n here. So I'm going to write it like this. And this I'm going to write it as 1 minus p to the power n minus k. Because I introduced an n to the power k, I'm going to take it out here. Now I'm going to take one of these into everywhere here. So I'm going to write this as n over n minus 1 over n, etc., n minus and this is lambda to the power k, and here also I'm going to write it as np over n to the power n minus k, and there is a k factorial here. So look at here, n over n is 1. This is 1 minus 1 over n, etc. This is 1 minus over lambda k over k factorial. And this is 1 minus lambda over n to the power n minus k. So if you want, you can write this as 1 minus lambda over n to the power k. So now what I want to do here is, I want to put limit n goes to infinity. There is no p here, only variable is n. So notice that when n goes to infinity, this factor goes to, this goes to 0, this goes to 1. All of this go to 1. This become 1. This stays as it is. This is, look, when n, this is a finite number, k is finite. So this is lambda over n is, n goes to infinity, so this goes to 0, this gets close to 1. A product of a finite number of ones, that's constant. Whereas here, so this term will be limit n tends to infinity. We can use this expression, 1 over x over n goes to e raised to minus x. So this goes to e raised to minus lambda. So the bottom line is this goes to lambda n over lambda k over k factorial e raised to minus lambda. So I'm going to rewrite this in this manner. So this probability of getting k events is, k rare events is governed by this problem. But here, because n is infinity, this k could go to this one. So this is the new probability rule. And so this is a new random variable. So we call this random variable to be Poisson random variable. That's the notation used. So Poisson is a special case of binomial where the parameter p goes to is small. In other words, the likelihood of something happening is extremely small. So this is like you can see the number of cars in a highway, very large number. The accident, any particular car getting into an accident on any day is extremely small. So the number of accidents on any day, any highway, wherever, or a bridge, is k of them happening is governed by this rule, rare events. So people getting shot or whatever, these are rare events, so it's sort of easy to model it by, or it makes sense to model it by Poisson, right? So for example, probability that nothing will happen is simply e raised to minus lambda. Now, before I conclude this, I want to mention one more random variable that comes out of